Hi, welcome to Module 2 of Video Lecture 3. In this one, we're going to elaborate a little bit on what we introduced in the last module, specifically instantaneous change. Now to do this, we're going to employ a bunch of geometry. Some people learn really well geometrically, not so well using sort of analytic notation. Some people the reverse. If you don't learn well geometrically, don't worry about it. We'll spend a lot of time just going through the algebra effectively of calculus, but if you do learn geometrically, this should help you get a good intuition for what exactly a derivative is. Okay, so I mentioned in the last lecture that the derivative in calculus in general was useful for understanding instantaneous change at a single point. And I drew a picture there. Let me draw a little smoother picture because they're easier to figure out. There you go. There's a smooth function, right? On this axis is x, on this axis is f of x. Or y, whatever you want to call it, doesn't really matter. Now, this is just a function, right? It's kind of quadratic, but it doesn't matter. It's a function. Now, let's say, let's leave that there on the board for a second and step back for a moment. Mention that discrete change is relatively straightforward, right? Let's start with discrete change that happens at discrete times, right? So something happens at time 1, and then time 2, and then time 3. Let's say you're playing some game, and at time 1 you get $2, and at time 2 you get $3, and so on. And let's say at each particular point in time you get an additional $1. It's a great game, right? Well, what's the change in the amount you get in each period? Well, between 1 and 2, it's $1. Between 2 and 3, it's $1, and so on. So I could calculate the change in how much I receive between periods in that manner, and it's simply $1. Or I might care about the change in total money I have, and that's varying by time, right? Between 1 and 2, it's $1. Between 2 and 3, it's $2, and so on. Sorry, between 0 and 1, you get $2, so you get $1. Between 1 and 2, you get $2 more, and so on. Any kind of change like this can be calculated pretty simply. When you have some discrete time between each point, the change can just be divided by 1. The change between any 2 points can just be divided by 1. That idea is more general. Let's say I have some change between any 2 points. If I want to know the average change between points, I can look like this. So the change between 2 points is just this. If x2 minus x1 is 1, so it's this discrete process that happens at every given time step, then that's sufficient to describe change. I can understand the change in the function between those 2 points in that manner. Let's say I wanted to find more of a proportional change. I could divide by the change in the function that led to the change, by the change in the variable that led to the change in the function, right? So the change in the variable is x2 minus x1 in the bottom there. The change in the function is the top, f of x2 minus f of x1. And dividing them gives me a sense of the proportional change in that function between 2 points. That form would actually be of interest to you, and probably is known to you. If not, if you haven't seen it like that, maybe you've seen it like this in the past. If you don't remember that, that's fine. I'll just tell you, that's the slope of a line. That's the slope of a line that connects 2 points. And we can do that pretty simply, right? We can draw it on our function. So let's take an x1, an x2, and let's go over here and do our f of x1. And let's go up here. Let's be symmetric. I'll call it f of x2 now. And now we have 2 points, and the line joining them, that's the slope of the line joining 2 points. It looks, and I'm going to draw a horrible line. It's even harder to draw a line on a tablet than it is on a whiteboard. Okay, that's supposed to be a straight line. But that's the line drawing those 2 points. This thing over here, often called m, is the slope of a line joining 2 points. The line itself can be represented like this: y equals mx plus b, where b is the intercept, the y-intercept of that line, which is defined as the point at when x equals 0. When x equals 0, this part is 0, so just b. So the y-intercept, the point at which the line intercepts the y-axis, is found by plugging in x equals 0 to the line equation, giving you just b. That's the slope of a line. It's probably one of the first things you learned in geometry back whenever you took that. Or if not, never. But that's the line, and that tells me the slope of the line. More generally, this line segment right there, gesturing at it pointlessly, this line segment that I'm now going to circle, assuming that was straight, that's called the secant. That's a secant. It connects 2 points on a curve. It's a secant. The secant, in effect, helps you understand the change in the function between 2 points. So that's discrete change, right? That gives you a sense of discrete change. Now, all last module I was talking about instantaneous change. How do we go from discrete change to a concept of instantaneous change? Well, the key problem here is the space between here and here, between x1 and x2 is discrete, right? It's discrete and positive. It has an actual real substantive value. If you want to find the change at a given point, we have to, in essence, shrink that space. So let's try into a picture and show how that happens. Okay, so I'm going to drop the axes and just draw the actual function. Make it as big as possible. Okay. And I apologize for the lack of ability to draw straight lines here. I'll try a little better with this one. The trick is putting your hand on the tablet. Okay, so that's a little better. That's a secant between 2 points here. Now, is that a good approximation to how the function is changing over here? It might be okay. Might not. It's not so bad, it turns out in this case. How about over down here? That's a little worse, it looks like, right? This is changing pretty slowly down here, but this is pretty steep comparatively. So maybe it's a bad approximation there. It turns out the secant approximates the way the function is changing to a better or worse degree, depending on the width between x2 and x1, between this point down here and this point over here. So how can we make it better? Well, we can make that width smaller. So let's try again. Let's connect these points. I can do it again. We can connect these points. And now, sort of conceptually, what happens if we make that line segment smaller and smaller and smaller? Well, at some point, the 2 points would blend into one. And would only intersect, and it's hard to see in this picture, but it would only intersect the line, the curve rather, at a single point, right? So the idea is you take these 2 points in the function and you put them closer and closer and closer together. And for any reasonable value of the distance between them, they're still separate points. But in the limit, as you put them closer and closer and closer together, they merge into a single point. Well, the line segment you get then is known as the tangent line. The tangent to a curve is a line that just touches the curve at a single point only. It intersects the curve at a single point only. And that tangent tells you the rate of change in the function, or rather the slope of the tangent tells you the rate of the change of the function at that point. Because at that point, the function has to change in pretty much the same way that the tangent is changing. Otherwise, you'd have more intersections with the line segment. And that's the tangent. And the tangent line is the line, well, the slope of the tangent line tells us how that function is changing at that point. And that's what we're going to be trying to find out. Is the slope of the line at a single point so we can understand exactly how the function is changing at that point. That's the instantaneous rate of change to be distinguished from the discrete rate of change. And really, in the end, that's all we're really doing when calculating derivatives. When doing half of all calculus, we're trying to understand the instantaneous rate of change of a function. For one dimension, which is all we're going to do in this part of the class, it'll look somewhat like this always. Maybe the function will be more or less complicated, but we're just trying to find out the slope of the tangent line at that point that we care about. And we're trying to do it for all points in the function to compute a derivative. When we move on in part 5 of the class to multivariable situations, we'll then be looking at more stuff. We'll be looking at slopes of lines in different dimensions, but we'll get to that. And we'll actually discuss that a little bit in this video lecture just to give you a heads up. But that's it. We're trying to understand the tangent line, the slope of the line that's tangent to the curve at a particular point of interest. That's it. Okay. Now before we go on and formalizing this idea using limits, we're going to take a brief step to talk about notation. Notation is important because it turns out the derivative can be represented by lots of different notation. People use different notation in their papers, and you have to be familiar with that when trying to understand calculus and read papers. But that's the next module. For this one, the focus was on tangent lines and secant lines and how as you shrink the distance between 2 points that represent the boundaries of a secant, you end up merging in one point. The slope of the line, the slope of the sort of limit of the secants is the tangent line, and the slope of that tangent line is our thing of interest. Thank you.